Here's how a nuclear reactor works, step by step. Step 1. Fuel. Inside the reactor core are fuel pellets, mostly uranium-235, packed into long metal tubes called fuel rods. Each tiny pellet holds an enormous amount of potential energy. Step 2. Fission. When a stray neutron strikes a U-235 nucleus, the nucleus splits, fission, releasing heat and more neutrons. Those fresh neutrons can split more nuclei. That's the chain reaction. Step 3. Moderation. Fresh fission neutrons are too fast to be efficient, so the core is filled with a moderator, usually water, graphite, heavy water, that slows neutrons down, making fission more likely. Step 4. Control. To keep the chain reaction steady, not too hot, not too cold, control rods slide between fuel rods. Made of neutron-absorbing materials like boron or cadmium, push them in, they soak up neutrons, and the reaction calms. Pull them out, power rises. In an emergency, they drop fully in to shut the reactor down. Step 5. Heat transfer. All that fission heat needs to go somewhere. A coolant, often the same water that moderates, flows through the core, picking up heat, without boiling inside the reactor vessel in many designs. Step 6. Steam cycle. That hot coolant passes its heat to a secondary water loop in a steam generator. The secondary water flashes into steam, spins a turbine, and the turbine turns a generator to make electricity. The steam then condenses back to water in a condenser, and cycles again. It's a glorified kettle driving a very big fan. Two common designs. Pressurized water reactors keep the primary water under high pressure so it doesn't boil in the core. Boiling water. Reactors let water boil right in the core and send that steam directly to the turbine. Simpler layout, different safety trade-offs. Containment matters. The core sits inside a thick steel reactor vessel, wrapped by massive concrete containment designed to hold pressure and trap radioactivity. Multiple barriers, fuel ceramic, metal cladding, the vessel and containment stand between radioactive materials and the environment. Safety systems watch everything. Temperature, pressure, neutron flux. If something drifts out of bounds, automated scram inserts control rods. Emergency core cooling can flood the core. Modern designs add passive safety, gravity, natural circulation, and pressure differences that work even without power. Fuel doesn't vanish. Spent fuel is hot, thermally and radiologically. It first cools in deep pools, then can move to dry casks. Some countries reprocess, others store for the long term. In the end, a nuclear reactor is a carefully balanced neutron economy that turns atomic splits into steady heat, and that heat into clean, reliable electricity. Tiny changes in centimeters and seconds control gigawatts for years. That's the core idea. Literally. If you want a part 2 on fusion or small modular reactors, tell me.